Hello. This is just a little snippet I didn't quite get on the last video, so I wanted to throw that in here. So what we're going to do is figure out the distance and displacement of a person that moves from the 90-meter mark to the 10-meter mark, and then ends up at the 50-meter mark. So displacement, if you remember from before, is final minus initial. So that is going to be 50, okay, minus 90. It'd be minus 40. And again, the minus 40 means that we ended up left of where we started based on our Cartesian system. If we look at the distance traveled, well, they traveled more than 40 meters. They started at the 90 and ended up at the 10, so that was 80 meters. 80 meters. And then they walked another 40 to end up at the 50. So the total distance traveled is equal to 120 meters. So the next introductory topic here is vectors. Vectors are simply something that has a quantity that has a magnitude and a direction, as opposed to a scalar. A scalar is basically just a number. It will have a unit usually, such as a length of 30 centimeters or driving 55 miles per hour or having a mass of 65 kilograms. A vector is simply a quantity that has that in addition to a direction. So if we were traveling 55 miles per hour, that's a scalar, but if we were to put a direction on it, 55 miles per hour south of west, then it would become a vector. So what kind of things would make sense to have a direction? And that's really the big difference with vector is it's got a direction. Displacement have a direction? Do you remember from before, the delta x? Yeah, it does, and we usually we use the sign positive or negative. So 5 meters north, I ended up 5 meters north of where I started. That makes sense. Mass of 65 kilograms, so I've got a mass of 65 kilograms north. Does that make sense? No, I don't really think so. So that mass is a scalar. Temperature, 35 degrees Celsius east. No, that one doesn't make any sense. That's a scalar. Velocity, driving 55 miles per hour north. Does that make sense? Yeah, that makes sense. Velocity is a vector. Force, I pushed with 5 newtons to the right. Would it make sense for force to have a direction? Sure it is, the way you're pushing or pulling. Does time have a direction? That's kind of just something to chew on. I don't know. Does time have a direction? Certainly not north or south or east or west, but probably forward, maybe. So different ways we can represent vectors. We can represent them with just simply words, 5 meters east. We can do what we were doing before with displacement, delta x is equal to plus 5 meters. So again, I've got my magnitude and my direction. Or we can simply use an arrow, and this is what you did freshman year. If you had me freshman year for honors topics in physics, we used length. Now we won't be getting out our rulers and protractors this year, so don't worry about that. We'll be using sine, cosine, tangent when that time comes, which is not this unit. The length of a vector arrow indicates the magnitude or the how much. So a longer arrow would represent a bigger magnitude, and the direction of the arrow is obviously the direction. So that makes so sometimes you'll see people wanting to specify that a certain letter, so F for force, is a vector, and they might draw an arrow on it. Sometimes in books that might be tricky to do, I guess. They just use a bolded F or a bolded whatever they want to represent as an arrow, as a vector. So I don't usually do this on the board. When we talk about vectors, it should be understood. Okay, so if you wanted to figure out the speed of an object and you didn't have a radar gun and you wanted to calculate their speed, what kind of things would you want to measure? Well, you would probably need to know how far they went, and you would probably need a stopwatch to measure how long it took them. So you need to measure distance and time. So the equation for speed, and we won't be using this form of the equation very often, speed equals distance over time. Now distance is not a vector, so speed is not technically considered a vector quantity. So what we're going to use more frequently is this form of the equation, v bar, and v bar means average velocity. This is the displacement over time. So these are similar equations. How fast equals how far divided by how long. Speed equals distance over time. And velocity equals displacement over time. Since displacement has a direction, it is a vector. Velocity is also a vector. So now the bar, I think I may have mentioned before, means that it's the average velocity. So it's just the average. So the equation that you're going to frequently see for v bar, or sometimes you'll see it as VAVG, V average, is displacement divided by time. Displacement divided by time. Normally the delta is left off here because it's understood that time is the time elapsed or the change in time. So you don't normally see that delta down below. So if I wanted to figure out the velocity and speed of a runner that follows that travels around in a path, a circular track, and they go 400 meters around this track, and it takes them 100 seconds, and we want to figure out what their average speed is and their average velocity. Well, the speed would be equal to distance over time. Now, it's a 400-meter track, so they went 400 meters divided by the time, which is 100 seconds. So 400 meters divided by 100 seconds gives us 4 meters per second. That's the average speed, and that is the average speed. I forgot to mention that. And we want to figure out their average velocity. Did I trick you? What's the displacement? Displacement 0. So the average velocity in this case would be 0 meters per second. Now we said displacement is a vector, it has a direction, and we've been using the plus or minus to represent the direction. Velocity, we said, is also a vector, it has a direction, and it'll be the same as displacement. So if something is traveling to the right, and we say to the right is positive, then it'll have a positive velocity. If it's traveling to the left in that same coordinate system, then the velocity will end up being negative. So if I wanted to use this equation in a simple example, what is the displacement of a car which drives with an average velocity v bar for 15 seconds? And I were to write that out. So this is how, since I can't do things on a whiteboard, this is pretty much how I'm going to be doing them. It's asking for the displacement. It gives us an average velocity v bar of 23 meters per second east, and the time is 15 seconds. So using our equation, v bar equals delta x over t, substituting in 23 equals delta x over 15, and then doing the algebra, we get that the displacement is 345 meters east. So that is just a quick example of using the equation average velocity equals displacement over time. A little bit more of a complicated example, we have a boat, and it's got two different legs of the journey. The first part of the journey, it travels at 10 kilometers per hour for 40 meters. And then the second leg of the journey, it goes twice as fast and travels at 20 kilometers per hour for 40 kilometers. Again, the same distance, but twice as fast of the speed. And we want to figure out the average velocity of the entire trip. Well, to figure out the average velocity, I need to know two things. I need to know how far it went, and I need to know how long it took. To figure out how far it went, that's the easy part. It went 40 kilometers, and then it went 40 kilometers. To figure out how long it took, I need to do a little bit more math. So I need to figure out how long this part of the journey took, and I need to know how long the second part of the journey took. So that's what we'll work over here. So the first part of the journey, the average velocity was 10 kilometers per hour, and the displacement was 40 kilometers. Subbing in v bar equals delta x over t, we get the displacement, or the time is equal to 4 hours. The second part of the journey, it moves twice as fast. It's moving at 20 kilometers per hour, the same displacement. V bar equals delta x over t. The displacement, or the time, is 2 hours. So the total time that it took in this case is 6 hours. So it went 80 kilometers in 6 hours. So, and we put that into our v bar equals delta x over t equation. And we get 80 kilometers divided by 6 hours equals 13.3 kilometers per hour. You might ask, well, it went 10 kilometers for a little while, and then per hour, and then it went 20 kilometers for a little while. Why is the average velocity not just in between these? Well, it was going 10 kilometers per hour for a longer period of time, which is why the average velocity is closer to 10 than it is to the 20. kilometers per hour. So that's why it's 13. Okay. A little bit on problems using speed and relative velocity, relative speed and velocity. So if we have two cars and they're both traveling, the red car is traveling to the right at 35 kilometers per hour. The car on the blue car is traveling 65 kilometers per hour to the left, and they're 100 kilometers apart. And what's the relative speed? Now, are these speeds going to add or are they going to subtract? Is the relative speed going to be 100 kilometers per hour, or is it going to be 30 kilometers per hour? Are those relative speeds going to add or subtract in terms of their collision? Well, they're going to add. They're traveling towards each other, so those speeds are going to add up. It's going to crash faster because they're both moving. Okay, and after 1 hour, okay, they'll crash, and this one will be 35 kilometers away from where it started, and this one will be 65 kilometers away from where it started. Okay, and that's what we just went through. This is the same time as if one car had been traveling 100 kilometers per hour and the other car had been stationary. They would still collide in that one hour. Now here we've got two cars. Now this time they're moving in the same direction. We've got a car traveling at 80 kilometers per hour and a car moving away from it at 30 kilometers per hour. So what am I going to use as the average speed here? Am I going to use 110 kilometers per hour, or am I going to use 50 kilometers per hour? Are they going to crash faster or more slowly because of the way that they're moving? I was being paged from above there for a second. Well, the fact that the red car is moving away means that the velocity is going to be subtracted, so the relative speed is going to be 50 kilometers per hour. And since they're 100 kilometers per away with a relative speed of 50 kilometers per hour, it's going to take them 2 hours to collide. So after 1 hour, the blue car will have traveled 80 kilometers per hour from where it started, or 80 kilometers from where it started. And the red car went 30 kilometers from where it started. And then after 2 hours, they're both going to collide at the 160 meter mark or mile mark, whatever it is. Okay, so at this point you can do the first worksheet in the packet. All right.